Okay, so we are going to start our meeting online, lesson for applied quantum mechanics. And, mm, and the first topic which we are going to study is uncertainty principle. The uncertainty principle says that the position and momentum of a particle cannot be simultaneously measured with arbitrary high precision. So if uncertainty in position is delta x and uncertainty in momentum is delta p, then their product will be always greater than or equal to h over 4 pi. And this rule is called Heisenberg uncertainty principle, and this x and p are called conjugate pairs of operators. So we have other conjugate pairs of operator like energy and time and angular position and angular momentum. Their product of their uncertainty is also greater than or equal to h over 4 pi as shown here. But to understand uncertainty principle, let's come back to position and momentum again. So this uncertainty is not because of our instruments or the method which we are using to study some object, but it is inherited in our system because of its quantum nature. In quantum mechanics, particles are described by waves. So you can see a wave here, this wave. It has a single frequency, wavelength, wave number, k, or angular frequency, omega. But it does not have a single position because it is, going from right to left, or actually it is extending all the way uh, in all the region. So in order to get something localized from wave, we need to combine lots of waves like here, and these waves have different frequencies and wave numbers, and this combination is called superposition. Actually it is simply adding up, and combining these waves, we get this object which we call as wave packet. This wave packet has a single, not a single, but a mean position, let's say x naught, and some uncertainty in position, which is delta x. Now this wave packet is made up from these waves. These waves, so they have some momentum range or wave number range, and the momentum, let's say the momentum, mean momentum is p naught, and the uncertainty in the momentum uh, will be, we can measure using minimum and maximum momentum. So let's say it's delta p. Now Heisenberg uncertainty principle says that the product of delta x and delta p will be always greater than or equal to this h over 4 pi. So I want to just come back to this delta x and delta p again. If we try to reduce the uncertainty in position, sorry, I need to get this text, not the text, but mouse. I'm sorry, I'm unable to get this marker again. I want to, yes, annotate here. So if we reduce the uncertainty in delta x, then the uncertainty in the momentum will increase. But if we try to reduce the uncertainty in p, momentum, then the uncertainty in the position will increase, so that the product is always greater than equal to h over 4 pi. In classical case, we are unable to observe this effect, uh, this effect, because uh, our sizes are very much larger than this um, h bar or Planck's constant, which is in the range 10 raised to power minus 34 joule second. So the uncertainty principle is important only for quantum mechanical objects which are very small and which have wave nature. So I will take a break here. So let's see what we were talking about. That okay, Heisenberg uncertainty principle. The material which I'm showing here, it is mostly taken from Levi, or if it is not from Levi, I will mention the source on the slide. As I mentioned here, these pictures are taken from. These pictures are taken from hyperphysics. Sorry. And another thing which uh, we will use later on is this phase velocity. Phase velocity, this omega over k, this is the velocity of a single wave, which has a single one frequency or wave number. And this group velocity d omega over dk, this corresponds to combination of waves with large number of angular frequency and wave number, which corresponds to our wave packet or a particle. And so we are going to use it later on. So let's go to the next slide. In the next slide. Okay. Sorry, I have come ahead. And in the next slide, we will see how we can use the uncertainty principle to understand the dispersion of a wave or of our signal. For your case, since you are studying electronics, in electronics you always try to transfer a pulse from one end of a cable to another end, or from one instrument to other instrument, and you want to keep that pulse undispersed, or you want that signal to maintain its shape from one end to the other end. Okay, so let's come back to quantum mechanics. So in quantum mechanics, the localizing the Gaussian pulse in real space will increase its width in the corresponding distribution in k space or momentum space. So this is, let me make the marker here. Okay, this is our, oh my God, sorry. I was going to do something else, but this is our probability distribution, which is a Gaussian. So how did we get this Gaussian? So let's come back to this wave packet. You see, this wave packet is a wave, but if I want to measure the probability, it will be square of waves. So it will be always positive waves, and it will give us a kind of a Gaussian here. So this Gaussian, we are starting with this gray Gaussian here, which has a very small width, delta x. This is the width, and this is the mean position. And I will explain this dispersion for a free electron. Remember, free electron, free means the potential is zero. So there was no potential. So this electron was moving freely in space. So for this free electron, we had obtained this dispersion relation omega k, which was related to k wave number by this equation. If we use our formula of group velocity and phase velocity, we get that the group velocity will be twice the phase velocity. So after some time, the wave would start to disperse. Okay, one more thing, that if group velocity and phase velocity are same, then the wave will not disperse, and all the waves will be traveling at the same speed. So the wave packet will be traveling along with these waves. But if group velocity and phase velocity are different, like in this case, that our group velocity is twice the phase velocity, then after some time our wave will start to disperse, and Like here, you can see that this after some time, the width of this envelope or wave packet has increased. It has become larger. This delta x has become very large. So this is what we call as dispersion. So wave is spreading out in space. It's moving towards right. So its position is changing with time. So this is, I have mentioned that I'm showing delta x here. So what happened to the momentum space? Okay, these are the formulas which are given in books to measure this probability in position space, and this is the probability in momentum space. So in the in, momentum space, let's see what happens to the corresponding what happened to the corresponding Gaussian distribution, which is the probability distribution. For gray part, when the delta x was very small, delta p, you can see that delta p is wider here. Sorry, my lines are not very straight. So this is delta, maybe I should use mouse. So this is delta p here, and this is corresponding delta x. So their product remains greater than h over 4 pi. And this is the formula which is showing relation between delta p and delta k. After some time, the wave moves to this location with higher uncertainty in x, but the corresponding wave also changes. Please don't pay attention to units, they were arbitrary. I didn't change them. So, but here the uncertainty in momentum is reduced. The uncertainty in x is increased, but uncertainty in momentum is reduced. So again, the product will remain greater than or equal to h over 4 pi. So the width of the wave packet increases with time, and so we see the dispersion. And I have given this link for a video. I think I have shared it with you previously in our online chats. And this video explains this dispersion in a very nice way. So I will take a break here. So